Welcome to SIT399 Assignment 2. I'm Quanganhpham, and I will be talking about linear programming sensitivity analysis. Consider a rather simple two-variable LP here. The objective is to maximize z, which is equal to 4x1 minus x2. Constraint 1. 3x1 plus 8x2 no less than 120. Constraint 2. 6x1 plus x2 no more than 160. Constraint 3. x2 no less than 10. Both x1 and x2 are positive. Parameters are coded as shown. Using graphical method, maximum value of z is obtained when x1 is 25 and x2 is 10, marked as point B. The feasible region is marked with a star. Currently A1 is equal to 4, and isopropyl lines have the form of x2 equal 4x1 minus z, and thus have a slope of 4. Constraint 1 is non-binding. Constraint 2 line has a slope of minus 6. From this graph, you can see that if isopropyl slope is either positive or smaller than minus 6, optimal solution stays the same. This corresponds to A1 being either positive or smaller than minus 6. If isopropyl lines have a slope within the range of minus 6 to 0, the optimal solution is shift to the point A, 0, 160. In this case, 0 is larger than A1, larger than minus 6. One takeaway from this analysis is that as long as x1 generates profit, it is always optimal to produce 25 of x1 and 10 of x2. Currently, C3 is equal to 160, and constraint 2 is binding. As long as the intersection of constraints 2 and 3, which is B, remains feasible, the optimal solution will still occur at that point. In order to make B infeasible, we need to move it to the left of point C, the intersection of constraint 1 and 3. When B and C overlap, C3 has a value of 90. We say, for any C3 no less than 90, the optimal solution is x1 equals C3 minus 10 by 6. x2 is 10. Because C has the coordinate of 40 by 3 and 10, x1 needs to be smaller than 40 by 3. The new optimal solution occurs at the intersection of constraints 1 and 2. We can now find x1 and x2 via a system of linear equations. x1 is equal to 8c3 minus 120 by 45. x2 is equal to 16 minus c3 by 15. As constraint 1 is currently non-binding, C2 only affects the optimal solution when B is no longer in the feasible region, which means C is to the right of B. When B and C overlap, C2 has a value of 155. We can say for any C2 value no more than 155, the optimal basis remains unchanged. If C2 is larger than 155, the new optimal solution occurs at the intersection of constraints 1 and 2. We can find x1 and x2 via another system of linear equations. In the book Operations Research, Applications and Algorithms, Winston defined shadow price for the ith constraint of the LP to be the amount by which the optimal z value is improved, increased in a max problem and decreased in a mean problem, if the right-hand side of the ith constraint is increased by 1. This definition applies only if the change in the right-hand side of constraint I leaves the current basis optimal. This leaves us with two smaller tasks. First, we need to analyze where is the range in which the right-hand side of the constraint does not affect the current basis. If we refer to the last analyses that we did, for example C3 analysis, the current basis did not change as long as C3 is not smaller than 90. Then we shadow the calculation on our shadow price. We already calculated that x1 is equal to C3 minus 10 on 6, and x2 is always 10. z is now equal to 4 times c3 minus 10 by 6 minus 10. Z is equal to c3 times 2/3 minus 50 by 3. Every 1 unit increase in c3 will increase z by 2/3. Our shadow price for the third constraint is 2/3. Thank you for watching.